Hi everyone, welcome to the first lecture of chapter 13, which is our last lecture for the course. Super exciting. So today we're going to talk about solutions. So we have a couple different types of solutions. One type of solution is a homogeneous or homogeneous solution, and that would be like when table salt is mixed with water. When that happens, right, like if you were making some salt water, it looks like the salt disappears, right? It dissolves completely. And so this mixture is homogeneous because it looks the same throughout. The salt's still there. Like if you drank some salt water, right, you would know it's salt water. Or if you boiled all of the water off, you could get that salt back, right? But the salt seems to disappear in the water, so it looks the same throughout. So that's how we define it as a homogeneous solution. And these homogeneous mixtures we call solutions. We don't typically use that term when it doesn't look uniform throughout. We'll use a different term. We'll use like mixture. But if it's a homogeneous mixture, we will call it a solution. The compound of the solution that changes state is called the solute. So this would be like the solid now gets dissolved into a liquid, right? And the solution's a liquid. So here in this particular example, this would be sodium chloride or table salt. The component that keeps its state, that's called the solvent. And in this particular example, that would be water. And water is often our solvent. We use water to dissolve all kinds of things. If both components start in the same state, so like if you're mixing two liquids together, whichever one you have more of, the major component, that will be the solvent. So say we were like diluting some acid, right? That can still be a homogeneous mixture because the acid's not, reacting with the water. We're just kind of dissolving the acid in the water. But usually when we do this, we're having a small amount of acid in a large amount of water. So the solute in that example would be our acid and the solvent would be our water. Like I said, a lot of times in chemistry, our solvent is water because it's cheap and it dissolves a lot of things. The only time you'd use a different solvent is if your stuff, won't dissolve in water, or if your reaction is maybe water sensitive. So here's some examples of solutions. So like you can have a solution where both things, your solute and your solvent are both gases. So if we have, if we're thinking about air, most of the air is nitrogen, but some amount of it is oxygen, a smaller amount. So we would say that the oxygen is dissolved in nitrogen, even though they're both gases, because the nitrogen, there's more of it, right? We say the nitrogen is our solvent and our oxygen is our solute. You can dissolve gases in liquid, kind of like, this says club soda or just like any kind of regular soda, right? We have dissolved carbon dioxide in our liquid, so we can dissolve gases in liquids. Let's see, other common examples. You've got, this one says vodka, so alcohol just in general. If you, again, like I was talking about earlier, kind of like the acid, right? You have a small amount of acid and a large amount of water for vodka or, any kind of alcohol. You have a small amount of ethyl alcohol and a large amount of water. Yeah, and then, you can have things like seawater, right? That would be like our salt water, where your solid is dissolved in your liquid. But again, all of these are going to look homogeneous throughout. You're not going to be able to see the individual particles. It's going to look almost the same. It's going to look kind of essentially like water. So solubility, we're going to talk a lot about solubility in this chapter, and this tells you whether something is able to be dissolved or not. So when one substance, right, your solute, dissolves in another, the solvent, then it's said to be soluble. So like salt is soluble in water. Salt dissolves in water. Bromine is soluble in methylene chloride. It dissolves in methylene chloride. If your stuff does not dissolve, then we say it is insoluble. So like oil, right, does not dissolve in water, so we say that oil is insoluble in water. And whether something is soluble or not depends on two things. One of them is nature's tendency towards mixing. And so we call this entropy. We'll talk about entropy a little bit more kind of later in this chapter. But in general, nature tends towards disorder. You can think of this term entropy as kind of being like disorder. And the entropy of the universe or of a system is always increasing, right? It's easy to make things disordered. Think about your bedroom, right? Your bedroom, it is very easy to throw all your clothes on the ground when you get home, throw your books in a corner, right? You have to input energy to order your system, to clean your room, right? So your room would tend toward disorder unless you actually input energy to, clean it or order it. So this is just kind of a thing in general, right? In nature, we have a tendency towards disorder. So that's entropy is working in the favor of things dissolving. More on that though a little bit later. The big one here, and the one that we're going to talk about today though, is the type of intermolecular attractive forces. That is going to play a large role in determining whether something dissolves or not. If something has, if your solute and your solvent have similar intermolecular forces, then your stuff is more likely to dissolve. If if you have something that's polar and something that's nonpolar, those are not similar attractive forces, and then it may not dissolve. So that's kind of going to be our focus. We're going to focus on this one today. So we have our major types of intermolecular forces. We have covered these already. One of them, right, was ion dipole. So this would be if you have a polar compound, so something like water, right? These little Mickey Mouse guys, they're how we typically show water. So ion dipole would be something polar and an ion. So that's how we dissolve salt in water. Our next one would be hydrogen bonding. So here we have methanol and water. So when you see these OH groups on these organic compounds, that's showing you that you have essentially a hydrogen bond that can be formed, right? You have a hydrogen that's bonded to a highly electronegative atom, and if it came into contact with another hydrogen or another that's bonded to a highly electronegative atom or a highly electronegative atom, then it can hydrogen bond. So water and methanol can form these strong hydrogen bonds because we have an OH group here. So the hydrogen is bonded to a highly electronegative atom and attracted to another highly electronegative atom. Dipole-dipole interactions. So this is when two polar molecules come into contact, right? Even though methanol here can hydrogen bond, it is also polar. So it does experience dipole-dipole interactions. So whenever we're looking at, saying what type of interaction something has, remember that hydrogen bonding is kind of a specific type of dipole-dipole interaction. It's a very strong type of dipole-dipole interaction. But if something can hydrogen bond, it can also form dipole-dipole interactions. So just keep that in mind. And then chloroform can't form hydrogen bonds because that hydrogen is bonded to the carbon, which is not a highly electronegative atom, but it is polar because of its shape. So it can interact with methanol through dipole-dipole interactions. Ion-induced dipole, which we didn't talk about much, but we did talk about induced dipoles. So if we have something like chlorine, right, or chloride, that is negatively charged. And if it comes near something that's nonpolar, like hexane, that negative charge will cause the electrons in the hexane, right, to kind of, run away from that side. They will be repelled from that negative charge. And so the electrons will kind of hang out on this side of the molecule. And when the electrons hang out on that side of the molecule, it makes this side partially positive, and this side, partially negative, right? And so we have an induced dipole because it came next to this chloride. So they can undergo ion-induced dipole. And if you look, I should have been referencing these before. These are the strengths of these intermolecular forces. Okay, so we're going right now from strongest to weakest. An ion dipole interaction is stronger than a hydrogen bond interaction, which is why salt dissolves so well in water, right? And then hydrogen bonding, dipole-dipole, ion-induced dipole, and then we've got dipole-induced dipole. So similar to the ion-induced dipole, right? If we have a partial negative on this side and a partial positive on that side, then it can cause, right, this induced dipole in something like xenon, that has lots of electrons, right? And so, the electrons in xenon would be repelled by that negative charge. They might hang out more on this side of the atom. And so this would be partially negative. This would be partially positive. So a dipole-induced dipole is fairly weak. And then, of course, we have our dispersion forces, which are quite weak. But if you're a nonpolar molecule, that's all you've got. That's all your options. So if you're trying to figure out if something dissolves, your rule of thumb is like dissolves like. If you have something polar, it's going to dissolve in something polar. If you have something nonpolar, it's going to dissolve in something nonpolar. If you've got something that can hydrogen bond, it'll dissolve really well in something that can hydrogen bond or something that's polar, right? In general, you're just kind of looking for something that looks similar, right? A similar structure in general. So if you know the structure of whatever you're trying to dissolve, right, your solute, then you're going to want to find a solvent that has a similar structure to your solute. And if you can't find one that's got a similar structure, find one that has similar intermolecular forces. So that's this whole like dissolves like. Please be warned though, if you tell me on an exam or on a quiz, this will dissolve in this because like dissolves like, I will not give you points for that. That is just like something that you're going to keep in your head that helps you remember how something dissolves. You need to talk about the intermolecular forces, the structures, right? Things like that. And we're gonna talk about that more in this chapter. So I just wanted to put that out there though. Do not write down as an answer like dissolves like. That would be a very low level answer. And again, that's something you can kind of think in your head, but don't write that as your answer. So when the solvent and solute structures are similar, right, the solvent molecules will attract the solute particles at least as well as the solute particles are attracted to each other. And we would like them to be, be attracted even more to the solvent molecules than they are to the other solute molecules. So just some kind of handy hints. So polar molecules and ionic compounds will be more soluble in polar solvents, right? Again, like dissolves like. If you've got polar stuff, try and dissolve it in a polar solvent. And again, our most common one here will be water. We use water a lot for polar molecules, for ionic compounds. And then nonpolar molecules will be more soluble in nonpolar solvents. And a lot of times we will use hexane as our nonpolar solvent of choice. But anytime, and this is when your organic naming comes in handy, anytime you see this like ANE, that's telling you it's a long, straight chain hydrocarbon, which means it is nonpolar. So things like octane or maybe, butane or pentane, right? All of those kinds of things. Those are all going to be nonpolar solvents. So here's some solvents. Water is superpolar, right? We have lots of hydrogen bonding that happens. Methyl alcohol is still pretty polar. Ethyl alcohol is still pretty polar. This starts to, as you start to lengthen this non-polar chain, then your molecule becomes less and less polar, but it's still polar for now. Acetone is pretty polar because of the shape of the molecule, even though that this C double bond O, we call this a carbonyl group, is in the middle of the molecule. It still ends up being pretty polar. Toluene and hexane are both nonpolar. Diethyl ether has some polar bits, some nonpolar bits. So we would use this for something that has kind of a medium polarity. Maybe a little bit polar, but not a lot of it polar, right? It's got some portions of the molecule that are polar and some that are not. And then carbon tetrachloride is another nonpolar, kind of bulky solvent. So these are some really common ones that we use in lab. So let's see this. Like dissolves like. If we are dissolving methanol in water, so again, methanol is CH3OH. Okay, so here is our water molecules, and as you can see, they're all showing, right, the hydrogen bonding. We've got the oxygen being attracted to the hydrogen that's bonded to that other oxygen, and so on and so forth. So here is methanol. So our structure of methanol looks like this. So methanol, because it has the hydrogen that's bonded to the oxygen there, right? A hydrogen is bonded to a highly electronegative atom, and as you can see in these, right, like our oxygen is bonded to that hydrogen, and then it's attracted to another oxygen. So this is showing you that methanol can hydrogen bond. And so these will actually form fairly strong interactions because water then can go and make hydrogen bonds with the methanol, right? And so this would dissolve really, really well. Methanol dissolves really well in water. They're both very polar. They can both form hydrogen bonds. They have a fairly similar structure. I know it doesn't really look like it, but you know, this, since they're both fairly small molecules that have that alcohol group on there that can form hydrogen bonds. They're fairly similar in structure, fairly, you know, similar in polarity, and so they will form, you know, a very nice solution. So we can use this, you know, knowledge of intermolecular forces to predict whether these particular vitamins or anything really is soluble in water or it will be soluble in fat, right? You've heard vitamins can be, you know, fat soluble or water soluble, right? So there's only like so much of certain vitamins that you want to take a day because they are water soluble. And if you, you know, take more than 100% of, you know, water soluble vitamins, it doesn't help you anymore. Instead, you're just going to kind of pee them out. But, you know, sometimes you can take a little more of the fat soluble vitamins and kind of store them. So this is helpful from a medicinal standpoint. But the way that you're going to determine this, right, water soluble vitamins will have polar functionalities, right? So they will be ones that have, you know, OH groups on them because we're looking to form those hydrogen bonds. We're looking to have those, you know, polar portions. Fat is very, you know, is more non-polar. It's got a lot of non-polar bits. So something that will dissolve well in fats will be a more non-polar vitamin, and something that will dissolve well in water, right? Water-soluble vitamins will have more of these OH groups. So go ahead and pause here for a minute and figure out whether you think these particular vitamins will dissolve better in water or in fat. All right, so for this first one, vitamin C, if you look, there are tons of alcohol groups, right? We got one here and here and here and here. We've got this carbonyl group that's polar, right? So that's got lots of polar pieces. It's got lots of hydrogen bonding that can happen, right? So this one, vitamin C, will definitely be water soluble. If we look over at vitamin K, it looks like it's got a lot of just kind of hydrocarbon pieces, right? We've got these little carbonyl groups which are a little bit polar, right? So it's a little polar, but the majority of the molecule is non-polar. It's got tons of carbon and hydrogen bonds. So this one we would predict to be fat soluble. If we go down to vitamin A, and again, look at the structure. It's got a ton of carbons and hydrogens, and we have one little tiny, alcohol group over here. But the majority of the molecule is going to be formed from hydrocarbons. So this we would predict to be fat soluble. Even though it's got that little alcohol group, most of the molecule is nonpolar, so we would predict that to be fat soluble. And then vitamin B5, we've got this carboxylic acid group, right, which has the, kind of alcohol functionality. We've got a carbonyl here, we've got an alcohol, we've got an alcohol. And so this one, I would predict, and we've got this guy here, that amine group that I almost missed. This I would predict to be water soluble. Even though it's got, quite a bit of nonpolar bonds, I think we've got enough going on here that can make hydrogen bonds that this would likely dissolve in water. Maybe not as well as vitamin C, but it should still dissolve in water. It should be water soluble. So that's how I would go about predicting this. So similar, right? Just not about vitamins. Now we just have some structures. And so this one says, decide if the following are more soluble in hexane or in water. So if we were to be soluble in hexane, right? Again, you're looking for this ANE ending. That tells you that this is a long straight chain hydrocarbon, and this is going to be non-polar. And water, right, we know is polar. So go ahead, pause here, try these ones out. All right. These, I think, are a little bit easier than the vitamins. Naphthalene, we have only carbons and hydrogens. So that is going to be a very nonpolar molecule. This one we would predict to be soluble in hexane. Formaldehyde is a very polar molecule. We have one carbonyl group and nothing to balance it out. That is quite polar. And so this one we would predict to dissolve in water. Stearic acid is one, that we see the long straight chain hydrocarbons. It's got a lot of carbons on it, and then it's got this little tiny polar end over here. But the majority of the molecule is nonpolar. And again, we're going to kind of go with the majority rules in these particular cases. So since the majority of the molecule is nonpolar, this would dissolve better in hexane than it would in water. So this would be an example problem. So explain the solubility trends shown in the table below. So these, the only thing that's different, right? They all have this alcohol group on the end. So this is methanol, ethanol, propanol, butanol, pentanol, right? And so the only thing that's different here is that each time we are adding on a methyl group, we're adding on another carbon and its associated hydrogens. And so methanol we talked about earlier, methanol dissolves really well in water. This term miscible, we haven't talked about this yet, but this term miscible, this is essentially the same thing as soluble. Miscible means that the liquid dissolves in another liquid. A lot of times we'll use the term soluble when we're changing the state of our solute. So like a gas dissolved in a liquid or a solid dissolved in a liquid. But if we're dissolving two liquids in each other, a lot of times we'll use this term miscible instead of the term soluble. They mean essentially the same thing. It's just miscible is typically just for two liquids. So methanol, like we said, dissolves fairly well in water because they're both really polar. And it dissolves a little bit in hexane, but not very much. And then as we go down, right, ethanol still dissolves, well enough in water. Propanol dissolves well enough in water. But butanol, right, doesn't dissolve, right? We have a solubility, an amount that we can dissolve. Pretty much for methanol, ethanol, and propanol, you can mix as much of those with the water as you want, and they'll dissolve, right? You can make solutions of differing concentrations. But as soon as we get to butanol and pentanol, right, there's a maximum amount of these that will dissolve in 100 grams of water. And so 0.11, 0.03, and so we can predict as we, if we kept going to like hexanol or heptanol, right? If we kept going down this chain or, adding on more carbons, that we would be dissolving less and less and less of these particular compounds in water. And that is because, right, this nonpolar chain is getting longer and longer and longer. And so as this nonpolar chain gets longer and longer and longer, right, your structure looks less and less like water. Your molecule becomes less and less polar. That nonpolar portion starts to become a bigger factor in your molecule than that polar portion. So over here on this other side, right, we have solubility in hexane. It says ethanol will dissolve, and all of these will also dissolve. And again, it's because hexane is a nonpolar molecule, and it's interacting with the nonpolar portion. So we would predict, that as you go down, as you're adding more carbons, this nonpolar chain gets longer on these alcohols, and it should dissolve better in hexane. But it looks like the only, from this particular table, the only one that doesn't dissolve very well in hexane is methanol, and that's because methanol is pretty polar. And so it's not going to dissolve very well in a non-polar solvent because they don't have those interactions. Okay. So this one says, predict which solvent will dissolve more of the given solute. Okay. So again, this is another point where I want you to pause, figure out will your solute, dissolve better in which of the solvents. So pause, figure that out, and then come back. All right, so sodium chloride we know is an ionic compound, right? And so our ionic compounds will dissolve best in polar substances, because when we put sodium chloride into, let's say water, it dissociates into its ions, right? And so these form complete charges, Na plus Cl minus. So it's going to look to dissolve in something that's got, partial charges at the very least. So the more polar our substance is, the larger those partial negatives and partial positives will be on the dipole. So we're comparing methanol and propanol here. Since methanol is a smaller molecule, right? It's got a smaller hydrocarbon chain. That alcohol group will have a larger effect on the polarity of the molecule. So methanol is going to end up being more polar than propanol. So sodium chloride will dissolve better in methanol because it's more polar. Ethylene glycol. So if we look, ethylene glycol has two different alcohol groups on it. Okay, and it's got a nonpolar chain in the middle. So will it dissolve better in hexane or in water? Hexane is a very long straight chain hydrocarbon, right? We've got 6 carbons there. Water can form hydrogen bonds and is a polar molecule. So if we look at ethylene glycol, it's got 2 different areas where it can form hydrogen bonds, and then it's got a very small nonpolar chain in the middle. Since the polar portions are still a large factor in this structure, we would expect it to dissolve better in water than in hexane because it's got that, the nonpolar portions on each side of a very small molecule. And then diethyl ether. Diethyl ether has an oxygen in the middle, and then it's got the carbon, the carbon chains on either side. It kind of looks like this. So it is a polar molecule, but it's not super polar, right? It's just got that oxygen in the middle, and it can't form any hydrogen bonds, right? Because there are no hydrogens attached to that oxygen. So it's kind of, maybe a medium polarity. It's a little bit polar, but not a lot of it polar. And so it says, will it dissolve better in water or ethanol? Water is super polar. Ethanol is not as polar, right? Because it's got some straight chain hydrocarbons going on. So we would predict actually that this would dissolve better in ethanol than in water because ethanol has more of a similar structure, right? Ethanol would have more of a medium polarity, kind of like diethyl ether. It's more polar than diethyl ether, but it's not as polar as water, right? So again, this is one of those instances where we're looking for kind of a similar structure to decide which solvent we would use. So our last topic for this lecture is how soap works. So we're going to talk about micelles, which are cool. So soap, like sodium stearate here, will have 2 different kind of areas on the soap. So this is our hydrocarbon portion. Okay, that's this C18H35. And then on the end, it's got a carbon that's double bonded to an oxygen and then single bonded to another oxygen, which would leave us with a negative charge here. So we add on a sodium or something like that to balance it out. But when this goes into water, that sodium breaks off and it floats away and it does its own thing. And as we know about net ionic equations, pretty much we can just kind of ignore sodiums because they are always soluble. So this molecule is going to float around with a non-polar area and a polar area. Okay, and so soap is used especially when we have things that are greasy or oily, right, or fatty, right? They have large non-polar portions, and so if this wasn't true, right, things that don't have these big non-polar portions, washing with water should be enough, right? As we've talked about thus far, water dissolves things like salt really well, dissolves ionic compounds really well, dissolves polar substances really well, right? And so water should be enough to dissolve any of those things. The reason that we use soap is to dissolve things that are non-polar, okay? And so soap will interact with, so like this kind of gray, these things here, all the gray and black stuff, that is going to be our grease or fat or whatever it is. And so the soap goes and will form these attractions, right? These London dispersion attractions to the grease by just kind of lining up with it. And so it will just line up with all of these grease molecules along the nonpolar chain, because the nonpolar chain here is attracted to these long nonpolar chains. All right, and so when it does that, it will leave these polar portions kind of stuck out at the end. And those polar portions are attracted to the water molecules. So what's really cool is that these, the soap can form these London dispersion forces with the grease and kind of pull those grease stains or whatever it is apart, and dissolve it in the soap essentially. And then the soap can be attracted to the water through these dipole-dipole interactions, or sometimes through hydrogen bonding interactions, depending on the soap. And so when that happens, if it'll go forward, there we go. When it happens, we've got these long, this is how we model things in chemistry. When we have to talk about long straight chain hydrocarbons, we draw them as squiggly lines. So this is our long straight chain hydrocarbon, and at the end, it's got these, this polar portion that can be, like I said, attracted to the water molecules. And so the nonpolar portion will be in the inside, and the water molecules can surround it and dissolve it. So like here, this, maybe this is your grease, and your soap can be attracted through the nonpolar portion on the inside, and then it will, form these big balls with the polar portion on the outside, which water can then dissolve all of those polar portions, and it can wash away the grease stain or the fats or whatever the case may be. So soap is actually really, really cool. And I never, really understood anything about soap, I guess, until I became a chemistry major and I took these classes, and it was like, wow, water is cool. Wow, soap is cool, right? You have a whole new appreciation for how the world works. So that's the end of this first slideshow for chapter 13 on solutions. So send me any questions you have, and I will see you guys next time.